So the next topic of discussion is fault tolerance in Apache Storm. So what happens when a worker dies? When a worker dies, the supervisor will restart it. If it continuously keeps on failing on startup and is unable to heartbeat to Nimbus, Nimbus will reassign the worker to another machine. Okay. So next is what happens when a particular node itself dies. In this case, the tasks which are assigned to that machine will time out and Nimbus will reassign those tasks to other machines. Next is what happens when the Nimbus or supervisor daemon dies. So the Nimbus and supervisor daemons are designed to be fail-fast processes, and those are stateless as well. So the Nimbus and supervisor daemons must be run under supervision using a tool, so that if Nimbus or supervisor daemon dies, they restart like nothing ever happened. So no worker processes are affected by the death of Nimbus or supervisors. So this is totally in contrast to Hadoop, wherein if a job tracker dies, all the running jobs are lost. So is Nimbus a single point of failure? If you lose the Nimbus node, the workers will still continue to function. Additionally, supervisors will continue to restart the workers if they die. However, without Nimbus, workers won't be reassigned to other machines when necessary. Okay. So how does a Storm guarantee that it does a data processing perfectly? So Storm provides a mechanism for guaranteed data processing even if node dies or messages are lost, which we have already discussed in the chapter on guaranteed message processing. So the next concept of Apache Storm is hooks. So Storm provides hooks with which you can insert your custom code to run on any number of events within the Storm. So you can create a hook by extending a base task hook class and overriding the appropriate methods for the event you want to watch for. Okay. So now we will move on to very important framework in Apache Storm, and that is Trident. Trident is a high level abstraction for doing the real-time computation on top of Storm. It allows you to seamlessly intermix high throughput stateful stream processing with very low latency for distributed querying. If you are familiar with high level batch processing tools, the concepts of Trident will be very similar. Trident has joins, aggregations, groupings, functions, and filters. In addition to this, Trident adds the primitives for doing stateful incremental processing on top of any database store. Trident has consistent exactly once semantics, so it is easy to reason about Trident topologies. As an illustrative example, let's look at an example of a Trident here. So this example will do two things for us. One is computing streaming word count from an input stream of sentences, and second is implement queries to get the sum of the counts for the list of words. So for the purpose of illustration, this example will read an infinite stream of sentences from the following source. So this spout cycles through that set of sentences over and over to produce the sentence stream. So here is the code to do the streaming word count part of the computation. So we have defined a new fixed batch spout here. In that we have fields called sentence, and these are the values for that sentence. And then we are setting this spout set cycle to true, so it will keep on cycling this set of input sentences. Then we are defining a new Trident topology here, and to this topology we are defining a new stream to which we are making this point to this spout that we have defined here. Then for each of this emitted tuples we are emitting a field called sentence. Okay, then we are splitting this sentence into each of the words. Then we are grouping by each of the word, and then we are aggregating the word counts with a parallelism of 6. Okay, so first a Trident topology object is created here, which exposes the interface for constructing your Trident computations. Trident topology has a method called new stream that creates a new stream of data in the topology reading from an input source. In this case, the input source is just like the fixed batch spout that I have defined here. So this spout is an input to it. Input sources can also be any of the queues like Kafka queue. Trident keeps track of a small amount of state of each input source in Zookeeper, and this spout specifies the node in the Zookeeper where Trident should keep the metadata. Trident processes the stream as small batches of tuples. For example, for the incoming stream of sentences, it might be divided into batches like this. So this is the stream of input sentences which we are emitting right now. So it can be partitioned into batches like this. So generally the size of these batches are in the order of thousands or millions of tuples depending upon how many input tuples are coming in. So Trident provides a full-fledged batch processing API to process those small batches. So the API is very similar to what you see in high-level abstractions of Hadoop. Okay, so Trident provides the functions for doing aggregations across batches and persistently storing those aggregations in the memory or in the DB. Finally, Trident has first-class functions for querying the sources of the real-time state. So back to the example, the spout emits a stream containing one field called sentence. Right? We have seen here that spout emits sentence. Right? So the next line in topology definition is split. So the split function, what it does is it takes the sentence field and it splits it into words. Each sentence tuple creates potentially many word tuples for the sentence. Okay, and this is how that split function is defined. It accepts the sentence and it splits that sentence into words with space as a delimiter, and it emits all these words. Okay, and your rest of this topology, after the split operation is done, the rest of your topology computes the word count and keeps the result stored. First, the stream is grouped by the word field. Then each group is persistently aggregated using a count aggregator. Okay, so this is how the aggregation is done. So the values which are stored by persistent aggregate represents the aggregation of all the batches which were ever emitted by a stream. Clear? So next we'll move on to the fields and tuples in Trident. So the Trident data model has a named list of values. During a topology, tuples are incrementally built up through a sequence of operations. Operations generally take in a set of input fields and emit a set of function fields. So the input fields are used to select a subset of the tuple as input to the operation, while function fields name the fields that operation emits. So consider this example here, wherein suppose you have a stream called string that contains the fields x, y and z. To run a filter called myFilter that takes in y as input, you will write it this way. So suppose the implementation of myFilter is like this. So this will keep all tuples whose y field has a value less than 10. So the Trident tuple given as input to myFilter will only contain the y field. Note that Trident is able to project a subset of a tuple extremely efficiently when selecting the input fields. The projection is essentially very fast here. So let's now look at how function fields work. Suppose we had this function. So this function takes two numbers as input, okay, and emits two new values. So the addition of the numbers and multiplication of the numbers. Suppose you had a stream with fields x, y and z, you could use this function like this. Okay, so you are passing x and y as the fields on which add and multiply operation will happen. It will read x, it will read y, it will add and multiply xy, and it will emit the result. In the added column it will have added value of x and y, in multiplied column it will have multiplied value of x and y. Okay, so this is how that operation is done using .each operator. So the output of the functions is additive. So the fields are added to the input tuple. So the output of this, each call will contain tuples with 5 fields x, y, z, and to that will be added multiplied and added columns. So totally earlier there were 3 fields x, y and z. Now after this operation it will have 5 fields x, y, z plus 2 more fields added and multiplied. Clear? Now with aggregators, on the other hand, the function fields replace the input fields. So this is the difference. In aggregate, the function fields replace the input fields. So if you had a stream containing fields value 1 and value 2, and you did this particular aggregate operation of summing value 2 and emitting sum field, suppose you do this, then the output stream will only contain a single tuple with a field called sum, representing the sum of all value 2 fields. So in aggregate, the output field replaces the input field. Next is with group. With grouped streams, the output will contain the grouping fields followed by the fields emitted by the aggregator. So for example, suppose you write like this. In this example, output will contain the fields value 1, okay, plus sum. As we have seen, what aggregate does, it replaces the input field with the output field. So value 2 won't be shown in the output. Sum will come in place of value 2. But in case of group streaming, the group by column also comes. So in this example, output will contain value 1 and sum. So the challenging thing in Apache Storm Trident is maintaining the state information, because we need to update the state information so that it is 100% guaranteed that we don't update the state information twice. For example, suppose we want to maintain a count of a particular aggregation in the DB by a batch. It should not happen that it updates the count and then a batch fails, because if the batch fails, then entire batch will be retried, and it should not happen that we update the count twice in the DB. Hence, to avoid this confusion, each batch is given a unique identifier called the transaction ID. So if the batch is retried, it will have exactly the same transaction ID. So while updating in the DB, a check is done whether the count is updated for the same transaction ID earlier, so that we don't update the DB twice. So the state updates are ordered among batches. That is, the state update for your batch 3 won't be applied until the state update for your batch 2 is already succeeded. Clear? So execution of the Trident topologies are done in very efficient way. So suppose we had this particular storm topology with us. Okay, so this is a spout, and then which is emitting a set of tuples, and then we have a dot each operator which is used of Trident for processing the tuples emitted by this spout. Then after we apply dot each operation, it will emit its own set of tuples, and this each will operate on output of the first each, and it will generate its own output. Then a group by will happen on this result, and then your persistent aggregate will do the aggregation operation and place it in the Trident state. Okay. On the other side, we have a spout which again emits set of tuples. So this each operation will process those, emit it to group by operation, and it will also emit to another path, another each board, okay, which takes in as this input and emits to partition by query. So these operations can keep on going on parallelly in the entire storm. So this Trident topology will get converted to like this. So here these are the dotted lines which I have shown as the groups of the entire topology. So this topology is a Trident topology which gets internally compiled into this topology, which is a storm topology. Clear? So with this we are completing on Apache Storm. In my next series we have more discussions on Kafka, which is a messaging system. Thank you.